Hello, this is Mr. Collier, and today we're going to be looking at combined events, which is basically probability of multiple events, multiple things happening, and there's several different cases we need to consider. Okay, so first we're going to look at independent events. Independent events do not affect each other, like a tossing of a coin. If you get like 10 heads in a row, that doesn't affect the next coin flip. You still have a 50% chance of getting heads, 50% chance of getting tails. So that's an example of a independent of independent events. Okay, so when you have independent events, and you want to find the probability of one event happening and another one, you just multiply them. For example, the probability of flipping two coins and getting heads and then heads. Well, the first heads is the probability of half. The second one is half. You just multiply them according to our rule here, and it's a quarter or 25% chance of you flipping two coins and getting heads and heads. Okay, so some more examples. Example one, if Aaron has a 60% chance of winning a tennis match, and Fred, I think I'm going to need my calculator for this one. If Aaron has a 60% chance of winning a tennis match, and Fred has a 75% chance of winning a tennis match, find the probability that they both win their matches. So I'm assuming here they're not playing against each other. Okay, so Aaron has a 60% chance and Fred has a 75% chance. So to get the probability that Aaron and Fred win, we have to take the probability of Aaron winning times the probability of Fred winning. Okay, which is, well, we can change these percents to decimals, 0.6 and 0.75. And I'm going to multiply that together on my calculator here. Just a second. Okay, quit out of that. 0.6 times 0.75 is 0.45. Okay, so that's a 0.45. You can leave our answer like that, or you can write 45%. What's the probability Aaron wins, but Fred loses? Okay, so the probability that Aaron wins and Fred loses, that's going to be, well, the probability of Aaron winning is 0.6. Probability of Fred losing is 25%. So that's 0.25. So we're going to do 0.6 times 0.25, and we will get 15, or 0.15. So that's 0.15 or 15%. Okay, so that's how we do that. It's just multiplying those probabilities together. Now, if we have mutually exclusive, or disjoint sometimes it's called, events, those are events that have nothing in common. So here's a mutually exclusive thing here. I've talked about playing cards. You can't get a card that's an ace and a king, right? But you could get a card that's a heart and a king. There's like an overlap here, okay? So this is not mutually exclusive, and this is a mutually exclusive case. This comes up when we have probability. This means probability of an event A happening. This means probability of A and B equals 0, so they can't be both. Alright, now this comes up with OR probabilities. When you have probability of A or B, which you might see sometimes like this, probability of A or B is equal to probability of A plus probability of B minus the probability of A and B. Okay, so that's for not mutually exclusive. Now, if they are mutually exclusive, then you can see that this thing is 0 anyway. So it's really the same formula. Basically, you have to add OR probabilities, and then you have to subtract the overlap, like you see in this Venn diagram, to subtract the probability of that one. Anyway, we're going to see some examples of that in a second. Actually, maybe we'll do that right now. Okay, so in a pack of playing cards. We have like 52 cards, right? So maybe we'll look at the probability of getting an ace or getting a king if you randomly pick a card out of the deck. Now there's 4 aces, so that's 4 out of 52. And there's 4 kings, so you add them. When we have OR probabilities, we add them. Now, is there any overlap? Is there a probability of A and B? No, not in this case. So we don't do the subtraction part. So that's it. It's just 8 out of 52. You can simplify that to, I think if you divide them both by 4, you get 2 out of 13. So it's actually 2 out of 13 probability that you'll get an ace or a king. 13, that's 14, I'm sorry. 2 out of 14. No, that's 13, sorry, I was right the first time. 2 out of 13. Okay, next we have this case. This is not mutually exclusive. So here we have probability of hearts or a king. Okay, so we're going to do probability of heart plus the probability of a king minus the probability of heart and king. Okay, so probability of getting a heart, there are 13. Well, actually it's a quarter, right? Because a quarter of the cards are hearts. So you could write down a quarter. Actually, I'm not going to write a quarter because I want my denominators to be the same. So I'm going to write that quarter as 13 out of 52. Okay, there are 13 hearts in the deck. So 13 out of 52 plus the probability of getting a king is, well, there's 4 kings in the deck, so that's 4 out of 52. But you have to subtract the probability of heart and king, and there's 1 card that's a heart and a king, so I have to subtract 1 out of 52. Okay, and if I do the math there, 13 plus 4 is 17, minus 1 is 16. So we have 16 out of 52. I can divide those and simplify. Let me show you how to do that with a calculator, though, in case you're really bad at fractions. I can go to alpha, then this y equals button here, and I can make a fraction. So that's going to be, I'll do 16 out of 52 here, and then press enter, and it gives me a simplified fraction. That's just 4 out of 13. So it's a 4 out of 13 chance of getting a heart or a king. Alright? Okay, next, we're going to look at dependent events. Okay, so this is for, I guess it's usually when we're talking about and. Yeah, and probabilities. Okay, so we looked at independent before. You just multiply them when we have independent events, right? So for dependent events, well, let's look at this formula. It's exactly the same, but your probability of this one here is going to be a little bit different. So the probability formula looks like probability of A and B equals probability of A times the probability of B given A. Okay, so that just means you have to look out for what happens after A happens. Something's going to change the probability of B's. Okay, and I'll show you what I'm talking about in a second with this example. A bag contains 15 red M&Ms, 25 green. If an M&M is chosen and eaten and the second one is chosen, find the probability that both are green. So when we work out these probabilities, it's not that hard. Probability of, green, eating a green one, then randomly picking another green one is, well, we just look at the probability of the first one. Probability of the first green one is going to be, well, there's 25 green ones and there's a total of 40. So it's 25 out of 40. Okay, and we multiply when we're doing AND probabilities. So we multiply by, now the second one is, see that what happens is it depended on what happened the first time. Now, there's not 25 candy left, it's 24 candy. 24 green M&Ms. And there's 39 total left. So this is what it looks like. Yeah, I could do some simplifying before I multiply. I could do that on the calculator too. Let me show that before I do it by hand. So I could just, go to alpha, y equals we can do 25, oops, what have I done there? Let's see if this works. 25 out of 40 times, and I do alpha, y equals, pick the first one, 24 out of 39. Oops, yeah, it doesn't work. I have to change this thing here. Can I just press delete? Yeah, it worked, I think. Okay, so it worked out. You multiply that, you get should get 5 out of 13. Okay, so let's just work that out manually in case you're interested in how to do that with the fractions. So 25 out of 40, I can divide them both by 5, I get 5 out of 8. And I can do 24 divided by 8 and get 3. Now 3 and 39, I can divide them both by 3 and I get, yeah, so you get 5 out of 13. That's right, 5 out of 13. Okay, so part B. In part B, it says probably the first one is green and the first one's red and the second one's green. So probability of red, then green is going to be, well, probability of getting red one is 15 out of 40. And then the probability of the green one, now there's still just 25 green ones left, but there's a total of 39. So that's how we work that out. Let's do some simplifying. We divide them both by 5 and we get 3, 8, and actually I divide these by 3, I get 1 and 13, and I believe that's it. You can't do any more simplifying, so you have to do 8 times 13. On the numerator I'm going to have 25. The denominator, 8 times 13 is 80 plus 24 is 104. Looks like about 25%. Right, so 25 out of 104, let me just try that in case you're interested. 25 divided by 104 is, yeah, it's about 24%. So actually I should use 3 significant figures since that's what we're supposed to be doing. So that's approximately 0.240. So that's about 24.0%. That's 3 significant figures. Or just leave it as a fraction, I guess, the probability. Okay, some more examples. Justine estimates the probability of passing the math exam is 0.8, like 80%, and its probability of passing English is 0.9. Assuming these two events are independent, find the probability that Justin will pass both of them. So that's like and. That means we're going to be multiplying. So the probability he passes both of them is going to be equal to, we'll have to multiply these together, just 0.8 times 0.9, which is 0.72, so about 72%, or exactly 72%, assuming it is correct. We'll pass math, but we'll fail English. That's also like an and probability. So we're assuming these are independent, so the probability is going to be passing math 0.8, failing English is 0.1, so I believe that works out to be just 0.08, which is about 8%, so it's a very low chance. Pass neither of them, so that means fail both of them. That's going to be probability is going to be 0.2 times 0.1, because there's a 20% chance of failing math and a 10% chance of failing English. We get 0.02. So only a 2% chance of failing both of them. Okay, next, an example from above. And the problem above, hang on. Okay, let's skip that one. A box of chocolates contains 4 chocolates with nuts and 8 chocolates without nuts. If 2 chocolates are randomly taken from the box without replacement, don't put them back. What's the probability that the first chocolate has nuts and the second one does not? So that's an important word there that tells you that this is going to be dependent because we don't replace them. So what's happening here is, so we're getting the probability that the first one has nuts and the second one no nuts. Alright, so there's 12 chocolates all together. So the probability that the first one has nuts is 4 out of 12. And now when we get the second chocolate, there's still 8 chocolates with no nuts, but there's 11 total in the box now. So I can do some simplifying before I multiply. Divide by 4 here, I get 1 and 3, and that's it. We're going to get 8 out of 33 is the probability there. What's the next one? We're going to have probably neither of the chocolates have nuts. Okay? So that's going to be, well, neither of them have nuts, so probability is 8 out of 12 that the first one doesn't have nuts. But now we have 7 chocolates with no nuts and a total of 11 in there. Let's do some simplifying. Divide these by 4 and we get 2 and 3, and that's it. That's all we can do. 2 times 4 is 14. 3 times 11 is 33. Okay. That looks fairly close to half, or 50%. Probably at least one of them has nuts. Okay. So for this one, probably at least one of them has nuts. There's a couple ways we can go about this one. We can get the probability of the first one having, so at least one of them has nuts, or probably the first one having nuts and the second one no nuts. We can do that, and we can add the probability of the first one having no nuts and the second one having nuts, and then add together the probability that both of them have nuts. Okay, that's all the possibilities in which at least one of the chocolates have nuts. But here's another thing we can do, a little bit easier. The probability that at least one has nuts is equal to 1 minus the probability that both have no nuts. Okay? Because those are complementary events. They have to add up to 1, right? There's only 2 possibilities. Either both of them have no nuts, or at least one of them have nuts. So that's what I'm going to do. And so probably both have no nuts. We actually worked that out in part B. So the answer here is just 1 minus 14 out of 33. And so that's just going to be 33 minus 14 is 19, right? 19 plus 14 give you 33. So it's going to be 19 out of 33, right? So those two numbers there add up to 1 because they're complementary events. Okay, in the next example, 1 ball is selected at random from a bag containing 5 red balls, 2 yellow balls, 4 white balls. Find the probability of selecting a red or white ball. So when we see or, we're going to add probabilities together. But these are mutually exclusive, because you can't get a ball that's red and white, so they're mutually exclusive. Okay? That means we don't have to worry about any tricky business here. They're mutually exclusive. All we have to do is add the probability of red plus the probability of white. So the probability of getting a red one is 5 out of, and the total is 11. And the probability of getting a white one is 4 out of 11. So the total probability is 9 out of 11.